Hey, it's Mr. Saltano, and this video is going to explain some unique properties of water. So first we have to talk about the bond between the hydrogen and the oxygen. So we've said in the past that the bond between the hydrogen and oxygen is a polar covalent bond. Something very different is something called an intermolecular force. So that's represented by the dashed line here. And intermolecular force occurs between different molecules. So we can see here that the intermolecular force that happens between water molecules is actually known as a hydrogen bond. Now this is really misleading actually because a bond is very different than an intermolecular force. Bonds are much stronger and harder to break. The only way to break a chemical bond, for example like this one, is through a chemical reaction. A way to break hydrogen bonds between water is actually just run your hand through the water. That would be simple enough to break the hydrogen bonds between multiple water molecules. And that's because intermolecular forces in general are very weak, bonds are much stronger. But another important point is that even though in general intermolecular forces are weak, the strongest among them that water utilizes is the hydrogen bond. So even though intermolecular forces in general are very weak, hydrogen bonding, which is not a bond at all, is actually the strongest among them, and that's going to lead us into all of the properties that we discussed in the video essentially. So just another example here, hydrogen bonds are a connection between the hydrogen atoms of one molecule and a highly electronegative atom of another molecule, but not a full covalent bond. So they're very different things essentially. So if we're looking at an example, a really important example of hydrogen bonding, this is the type of bonds that happen between adenine and thymine, and also guanine and cytosine in your DNA essentially. So if we're looking down the middle of the double helix, we can see there's 2 hydrogen bonds between T and A and 3 hydrogen bonds between G and C. So this is a really important example of hydrogen bonding. It also happens between in your proteins in your body that make you. These hydrogen bonds also occur there, so they are very important for us to survive and live essentially. So one property of water that utilizes hydrogen bonds, and a really important property, is called surface tension. Technically, surface tension is the force required to break the surface of the liquid, and what we want to know is that water has a very high surface tension. So looking at exactly what that sort of means, if we're looking at a water molecule in the middle of a water droplet, so here's sort of our zoomed in picture of what would be a regular water droplet, the middle water molecule is being pulled in equal different directions. But if we look at the water molecule on the top, it's actually just being pulled more down to the left and to the right into the water itself. What happens when that happens is that, I just imagine it sort of like the water molecule pulling to the left and the water molecule pulling to the right. Even if we just think of those ones, we're seeing it pulling on all sides essentially except for the top. And as a result, what happens is it ends up being sort of like the top of a drum. We know that the pulling in a drum is mostly happening on all sides except for the top, and so that creates sort of a tension there that allows you to place your drumsticks on the drum, for example. It allows for a lot more force to be pressed down onto the drum. Same thing with water. So water has a very high surface tension because the attraction from one water molecule to another water molecule is strong enough that the other molecules pull on that one molecule, and between them it creates sort of a skin on top of the water, and it allows for things like water striders to walk on top. And also, if you want to try this at home, if you're very careful and you don't mix the oil of your fingers with a paperclip, you can actually rest the paperclip on top of clean water. So this is because of surface tension that this happens. I also wanted to just show an example of what this looks like in space. Without gravity pulling water down, it's very interesting to watch how the water holds itself together because of surface tension.
I filled a water bag. This has drinking water in it. And I'm going to squirt a bunch of water into this washcloth. Okay, so here's a soaking wet washcloth. Get the microphone so you can hear me while I'm talking. And now let's start wringing it out. It's really wet. It's becoming a tube of water. The water is all over my hands. In fact, it wrings out of the cloth into my hands. And if I let go of the cloth carefully, the water sort of has it stick to my hand. Okay, so the experiment worked beautifully. And the answer to the question is the water squeezes out of the cloth. And then because of the surface tension of the water, it actually runs along the surface of the cloth and then up into my hand, almost like you had jello on your hands or gel on your hand.
Another example is capillarity, or also known as capillary action. And this is really important because this is what allows plants and trees and things like that to pull the water up from the roots where they normally get it, and it allows the water to travel through up to the rest of the plant. So it's the rising of a liquid through a narrow tube. Here's an example of some celery that was placed in food coloring water. And the celery is of course not naturally red, but the food coloring water is red, and we see the water has actually traveled up through the celery because of capillary action, and it's actually gone into the leaves and turned them red. So this is something that liquids can do, and water is very good at it. And if we look at the meniscus of water, we're used to measuring the volume of water in a graduated cylinder looking at this meniscus, right? Looking at the bottom of this dip. Water forms what's called a concave meniscus because the water is actually more attracted to the glass than it is to itself. And then so that's causing that to happen. If we look at a different example, actually Mercury is more attracted to itself than it is to the glass. And so this is called a convex meniscus. This is almost like an upside down meniscus where it's pointing upward. And you can sort of imagine that the mercury is actually piling up on top of itself, trying to touch the glass as little as it possibly can. But yeah, so capillarity is the ability of the liquid to travel through a narrow tube. Another very big one is the density of water. So something very unique to water, sort of interesting. If we look at liquid water, here's our picture of liquid water. The molecules, just like any other liquid, will slide past each other, right? And they're relatively compact. What's sort of unique to water is as the water begins to freeze, and when it does freeze, the water separates and orients itself into these hexagon shapes. You have multiple water molecules, and they all always do this, and as a result, you're creating a lot of space between the water molecules that form the ice, essentially. Space that wasn't there in the liquid form of the water. So what that means then is that the density of the water, if we're looking at this, the density of regular water is just regular M over regular V. And then if we look at the density of the ice, we're taking the same M, same mass of water, but we're dividing by a larger V, a larger volume, because the water's taken up more space now. As a result, if we take the same numerator and divide by a larger denominator, then our number goes down. So this is very unique to water in the sense that actually as it freezes, it becomes less dense. This is counterintuitive because you think, oh, ice is hard, so it must be more dense. But if we do our ultimate test, right, things that are less dense will float, things that are more dense will sink, we can see that ice actually floats. So ice is actually less dense in its solid form than in its liquid form, which is not normal. So this is another unique property of water. And again, it's happening because of this hydrogen bonding that forms these hexagon shapes. And something else that's interesting is that water actually has its highest density at 4 degrees Celsius. So it's actually the most dense in particular at 4 degrees Celsius. Not at 0 when it freezes, but actually still in liquid form at 4 degrees Celsius is when it becomes the most dense that it can be. So density of water. And also something else that's important to that is without water's ability to do this, fish would not be able to live through the winter. So what does that mean exactly? Well, if we're looking at warmer months, essentially, we can see that, of course, the warmer temperature water is on top because it's exposed to the weather. And the coolest water is on bottom, right? Fish are fine for that. But then during the winter, what happens is that the coldest water at the top stays floating at the top. And so it stays floating at the top here. Here's our dark layer of ice. And so because of that, the fish are insulated and they can actually stay warm enough to live during the colder months. Think about if the opposite happened. Think about if ice actually sank. The water at the top would freeze, and then it would sink to the bottom, and then that would form sort of a layer of ice at the bottom, and then more water at the top would freeze, forming another layer, until eventually the whole lake would freeze over. So without water's ability to float as it becomes ice, fish would not live through the winter. So this is another important quality, another unique property of water that's really important. Something else that's really important is water-specific heat. So specific heat, the amount of energy required to heat a substance by 1 degree Celsius. So different substances take a different amount of energy to heat them up. It's just something that's unique to each substance. Here we look at if we have a certain amount of energy applied to both gold, a kilogram of gold, and a kilogram of water, applying the same amount of energy to both. The gold would climb from 20 degrees Celsius to 90 degrees Celsius, and the water wouldn't really climb very much in temperature at all. The reason is because water has what's called a very high specific heat. It takes a lot of energy before water will climb in actual temperature. Other substances like metals get hot really quickly. Here's just sort of a table comparing those. Substances each have their own different specific heat, also known as heat capacity, and so they're all going to be unique in that way, and water is unusually high on the list essentially. It's got a high specific heat. So another reason why this is really important is because if you think about if you go to the beach and you touch the sand, it's a certain temperature outside, right? You go to the beach, let's say it's a hot day, touch the sand, and the sand might burn your feet, right? But then if you touch the water still feels relatively cool. And that's for the same reason. So they both have the same amount of heat applied to them, the water and the sand, but the sand has a low specific heat, a low capacity for how much energy it takes to heat it up, so it climbs in temperature dramatically. Whereas the water has a very high specific heat, same amount of heat applied to it is actually going to make it not climb that high in temperature. So unique property of water has a very high specific heat. This is also important because if you live in a desert area where there's no water, the days are extremely hot and the nights are extremely cold because water helps moderate temperature in general. If you live on the coast like we do, temperatures don't shift nearly as dramatically during the day and during the night because we have water around us to help moderate that temperature and keep things relatively constant. Second to last one, boiling point. So we just want to be aware that along the same lines, compared to these other chemicals that are of very similar size to water, water has by far the highest boiling point. So water has an unusually high boiling point compared to other molecules its size, and that's again owing to that hydrogen bonding that we see in water. Lastly, water is thought of as the universal solvent, meaning that it's very good at dissolving things. It's very hard to find pure water in nature because it dissolves ionic compounds and polar compounds like sugar very well. Other chemicals do not dissolve nearly as many substances as water is able to. So these are the reasons why water is unique. Thanks for watching, and remember, chemistry is everywhere.